In this section, we're going to talk about how to use double angle and half angle identities to find certain trigonometric function values. You don't have to memorize all of these identities, although they're not that difficult to come up with if you know how to manipulate the algebra. But I will leave a copy or a file that you can print on Blackboard where you can just have all those handy. So I'm gonna place the ones I'm using for each example nearby, like for this one, but it'll be a sheet you can print where all of them will be there. So that file will be there on Blackboard. Let's look at this example. We're gonna use a double angle identity first. If we are given a function value, like the cosine of theta is 3/5, and we're told the sine of theta is negative, we want to find the double angle of sine 2 theta, cosine 2 theta, and tangent 2 theta. So if cosine theta is 3/5, but sine is negative, right? So then let's draw a little reference angle here. So if cosine is 3/5 and sine is negative, so cosine could be positive in quadrant 1 or in quadrant 2, but sine isn't negative in quadrant 1. It's negative in quadrant, 4, so 1 and 4. So the angle we're looking at is got to be this one right here. So this would be 3. And this will be 5. And if you use the Pythagorean theorem, you would find that this is 4. But since it's down here, it's negative 4. Okay. So remember that sine is negative. That means it's this configuration right here. Now, why do we need to know sine? Because we're gonna use this sine 2 theta and then cosine 2 theta, and they both involve sine in the formula. So let's begin with sine 2 theta. That's equivalent to 2 sine theta cosine theta. And then we just plug in the values. So sine theta, according to this, is opposite over hypotenuse. That's negative 4/5. And cosine theta, we were given cosine theta as 3/5. And if you multiply those, you will get negative 24 over 25. So that's sine of 2 theta. Cosine of 2 theta, we will be using, you can use this one or this one. I'll just use this one right here to make it a little bit different. So that'll be cosine of square theta minus sine squared theta. And then you plug in the values of cosine and sine. Cosine is 3/5, so 3/5 squared. And then sine, we just used it right now. It's negative 4/5 squared. And so that'll give you 9 over 25 minus 16 over 25. And 9 minus 16 is negative 7 over 25. And then finally, for this example, we don't need to, well, you could use an identity if we knew what tangent theta is. So you could go divide sine theta, negative 4/5, and divide it by cosine theta, 3/5, get tangent theta, and then plug them in here. But I'm just simply going to use the general identity that tangent 2 theta must equal sine 2 theta divided by cosine 2 theta. Okay, like that's the same as tangent 2 theta. And I have those values already from here. So that'll be negative 24 over 25 divided by negative 7 over 25. which simplifies to 24/7. All right, let's continue with our lesson here. So this example is asking us to find the values of 6 trigonometric functions of theta, given that cosine 2 theta is 4/5 and theta is between 90 degrees and 180 degrees. So to be able to find the 6 trigonometric functions of theta, we need to find out what theta is. Theta alone, not 2 theta, right? So one of the identities is cosine 2 theta is 1 minus 2 sine squared theta. Okay, so we know cosine 2 theta is 4/5. So we plug it in there. And then we're going to solve for theta here. So we're going to subtract 1 and then divide by -2. So if you subtract 1 from 4/5, that gives you -1/5. And then divide by -2, that'll give you positive 1/10 equals sine squared theta. So now we're going to take a square root, right? We're going to take a square root. But every time you take a square root, there's a plus or minus involved. So we got to determine if this was plus or if this was minus. Since it terminates in quadrant 2, right? Theta terminates in quadrant 2, then your sign will be positive because all signs are positive in quadrant 2. So when we take the square root, sine theta will be the square root of 1/10, which simplifies to the square root of 10/10. And once again, it's positive because it terminates in quadrant 2. And so let's do a little illustration here in case this will help. So this is theta. And it terminates, again, between 90 and 180, which is right there. The sine of theta is 1 divided by the square root of 10, but we simplify to this, we rationalize to this. So it was really this, 1 over the square root of 10. And then if you do the Pythagorean theorem, you'll get that this is -3, okay, using the Pythagorean theorem. And now we have all the information we need. So the sine of theta was that, and the cosine of theta then is -3 over the square root of 10. Remember, we cannot leave a square root in the denominator, so we rationalize it to -3 square root of 10 over 10. And then similarly, the tangent of theta is opposite over adjacent. That would be -1/3. And then the other ones are just reciprocals of those, right? So let me just write them here. Cosecant theta is 1 over sine theta. Sine theta is 1 divided by the square root of 10. And so that reciprocal is the square root of 10. And secant theta is the reciprocal of cosine theta. And cosine theta was -3 over the square root of 10, which is negative square root of 10 divided by 3. And then finally, for this one, cotangent theta is the reciprocal of tangent theta. So it's 1 divided by -1/3, which is -3. Just like we simplify some of those expressions with square roots, sometimes you got to simplify an expression algebraically using double angle identities. So like this one right here. One of our double angle identities is cosine squared 2a or 2 theta is cosine squared a minus sine squared a. So we're going to use this one to simplify this one here. So in reverse, right? So we're going to have this over here, and that's going to equal that. So cosine squared of 7x minus sine squared of 7x is equivalent to cosine of 2 times 7x, which simplifies to the cosine of 14x. So using another double angle identity, we can use it to simplify letter B. So the sine of 15 degrees times the cosine of 15 degrees. There's a double angle identity that says this, that the sine of 2a is equal to 2 sine a cosine a. So we have sine times cosine, which is this. So we just got to get rid of that 2. So we actually divide by 2. And that gives us 1/2 sine of 2a is equal to sine a cosine a. And we're going to use this now to simplify it like this. So then the sine of 15 degrees times the cosine of 15 degrees is equal to 1/2 the sine of twice 15 degrees, which is 1/2 times the sine of 30 degrees. And the sine of 30 degrees is 1/2. So 1/2 times 1/2 is your answer, which in this case is 1/4. Sometimes you want to write an expression that's in a multiple angle. This one's a triple angle, 3x, but you want to write it in terms of a single angle. And you use double angle identities, right? A multiple angle identity. So let's do that for this one. So we want to write this in terms of just sine x. So the sine of 3x, we're going to write it as the sine of 2x plus x. And so using those summative identities that we did in a previous lesson, this becomes sine of 2x times cosine x plus cosine 2x times sine x. And then each of these, the double angles, we use the identities that we're using for this lesson. So for sine 2x, that's 2 sine x cosine x. And then we're multiplying that by cosine. And then cosine 2x is an identity that we used a while ago, cosine squared x minus sine squared x times sine x. And so if we distribute here, we're going to get 2 sine x cosine squared x. And then we distribute the sine into both of these. That'll give you plus sine x cosine squared x minus sine cube x. So the first two terms here are like terms, so we can combine them. That's 2 and 1, that'll be 3 sine x cosine squared x minus sine cube x. Notice we're still not all in terms of sine. We have that cosine, but using one of the identities, cosine squared is 1 minus sine squared x. So we substitute for that one. Then we distribute. That'll be 3 sine x minus 3 sine cubed x, and then minus sine cubed x again. And now the last two are like terms. So that'll be 3 sine x minus 4 sine cubed x. And that's your solution there. That's in terms of sine x with a single angle in there. All right, here's another set of identities. They're called product to sum identities. And it just depends what type of problem you're doing. You got to use the correct one. So for this one, it's a product of 4 times cosine and sine. So we're going to use this bottom one here, cosine times sine. So let's get to it. So that'll be 4 cosine of 75 degrees times sine of 25 degrees. So that'll be 4, and then we copy this right here. So 1/2 times, and I'm gonna separate the 1/2s. So don't be confused by that, please. So I'm basically distributing this 1/2 to both of them. So I'm gonna do the 1/2 for this one. And then the 1/2 for this one. And then we just simplify that. That's 4 times 1/2 sine of 100 degrees minus 1/2 sine of 50 degrees. And now we distribute the 4 to both of them. So 4 times 1/2 is 2. And minus 2 sine of 50 degrees. So that converts a product of trig values into a sum or difference of trig values. So if we just did a product to sum, we can also do a sum to product, like this one here. So again, sum means add or subtract. So this one is subtract. Subtract is sum, it's just sum of the opposite. So it's kind of thrown in there as an understood sum, but it's a sum of a negative, right? Which is a subtraction. So let's do it here. So sine of 2 theta minus sine of 4 theta. So that gives us sine 2 theta minus the sine of 4 theta equals, so I'm going to use the second one here. Okay? This one right here. So that gives us a 2 cosine. So first we're going to add them. 2 theta plus 4 theta divided by 2 times the sine of 2 theta minus 4 theta divided by 2. And so that gives us 2 cosine of 6 theta divided by 2 times the sine of -2 theta divided by 2, which is 2 cosine of 3 theta times the sine of -theta. And remember, sine theta is an odd function. And an odd function means that the sign of the negative argument is what's inside the parentheses here. That's equivalent to the negative sign of the positive argument. So because it's an odd function, so I'm just going to put the minus outside. And then this becomes positive theta. Now, this didn't specify that they got to be single angles. They just got to be as a product of two functions. So this became as a difference, which is the sum of an opposite, and now it's a product using those sum to product identities. And then the last example we're going to do here is using a half angle identity to find an exact value of a trig function. So find the exact value of the tangent of 22.5. And you could really use any of those identities if you knew, certain values that maybe are more easier to plug in than if I use this one. So as you can see, there's 3 different ways you can find tangent of a over 2. But for this one, it's sort of straightforward to use this one. So let's try doing this one here. So the tangent of 22.5 is equivalent to the tangent of 45 degrees divided by 2. So A is 45 degrees in this one. And 45 degrees is a straightforward value for sine and cosine. And that's one reason we would want to use this. So the sine of 45 degrees over 1 plus cosine of 45 degrees. Now, you still got to do a bunch of simplifying, but that's just arithmetic. So the sine of 45 degrees is the square root of 2 over 2. And so is the cosine of 45 degrees. Okay. And then on the denominator, you want to get rid of that denominator of 2 of this one. And you also want to get rid of that 2. So one way to do that is by multiplying the top and bottom by that denominator. And this will work because you're doing the same number to the top and the bottom. Okay? And therefore, when you multiply that, that'll get rid of the denominators for the fractions. But you also multiplying this 1 right here. So 2 times 1 would be 2. And then this will be plus the square root of 2. So that takes care of the intermediate denominators, but we still can't leave this that way. We have to rationalize it. And you rationalize it by multiplying by the conjugate. And if you multiply by the conjugate, then that'll give you 2 square root of 2 minus 2. And then on the bottom, if you do the conjugate rule, you square the first and you square the last, and you subtract them. That'll give you 4 minus 2, which is 2 square root of 2 minus 2 divided by 2. And we just have one last step to do here because we got to reduce everything by 2. So factor out a 2 on top. And then you're allowed to now cancel those 2's. And so that'll give you your answer for this problem.